Hi everyone, what we're going to be doing today is we are going to continue where we left off last video, which is essentially showing that there's some use to the Laplace transform of e to the at. So as you see, I want to save some time, so I already wrote the kind of basic things I'm going to be discussing today. So don't worry, I'm going to explain everything here, don't worry. So indeed, e to the at is a very important function, because when you put it together with the f of t, then what happens to the function with respect to time is it shifts. It basically shifts. So what you end up having is you end up having a function with respect to s, a function converted from time to s, but with s shifted, so the frequency is shifted. So it's quite interesting. Can't really think on top of my head of any applications might have, but yeah, I'm sure we can, if you're interested in the physics, we can Google some stuff. And a clue, it's probably to do with telecommunications, wave analysis, signal processing, all that kind of stuff. But I'm not going to delve into that. I'm just going to do the actual maths. And I know that this channel is meant to be about physics as well, but this series is about maths, so I might have a series that kind of shows the relationship between the maths and the physics behind integration or kernels, and that's because many of them are related to physics, like interchangeably. So yeah, I'm just gonna delve into it right now. So what we're doing here is we're trying to solve the Laplace transform of e to the at times f of t. That's what we end up having. As you remember, well, I hope you remember, that simplifies to this here, over here, e to the a minus s of t, right? If this looks familiar, this exponential function and the function multiplied by that, within that realm of an improper integral. And now we're going to see why it seems familiar. It seems familiar because this thing over here can be presented in a very snazzy form here as follows: e to the minus brackets s minus a of t. And why do we like this? We like this because this is very similar to a very definition of a Laplace transform. That is what I just wrote. So perfect. We just multiply the function by an exponential, and then look what we have. We essentially have a form that's analogous, that's very similar to the very definition of what we're trying to do. So what I'm going to show you is what exactly we're doing here. Because as you can see, s has been replaced by s minus a. And what does that mean? It means a can be viewed as some sort of, I don't know, perhaps retention constant. There's a retention factor. So why not have a retention constant? By how much this is going to be delayed. And what we're going to show here is we're going to use this definition here. And we're going to show that if you have a function and you apply a Laplace transform of it, so you have it times the e to the at, and we try to find it, and what you have here is you end up with a f of s minus 3. So it's the same function, it just takes a different argument. It takes s minus 3 rather than s. And s minus a, sorry. I know where I got the 3 from. And what we have here is we're going to show what we have here is an incredibly powerful result, which you can just kind of stick to different parts, and the result I'm going to get now. So for the first time, I'm actually going to show you an example, because this looks great, but just to let you know that it's not that confusing. I'm going to give you an example, and I'm going to say that f of t is equal to sine of t. We have no problem if we're finding the Laplace of that. We know that that is equal to. We know that if we find the Laplace transform of this, it's going to be equal to 1 over a squared plus s squared, or some respects in a different order, but the same thing. Well, what we're going to do now is we're going to show that actually for a function like f of t equals e to the 3t, for example, of sine of t, it's not that difficult to find the answer here. We're just doing finding the Laplace transform of that. It's essentially the same thing as finding regular sine of t here, except we replace the s term with s. You're going to replace it with s minus 3, and that's where I got it confused here. I was just thinking ahead. So minus a, s minus a, and that's fine. We don't need to open the brackets, expand anything. That's okay as it is, because actually this number here could be very big, it could be very large, and in many cases it will just make your answer look less presentable. So we're just going to leave it like that. Okay, so that's it for today. Don't have much to show other than that. So the next video is going to be about linearity of Laplace transform, and then I'm going to show you possibly the apex of challenges we experience in the Laplace transform. I'm going to show you how to use it in a differential equation. It's very long. It takes a lot of time, but it's the most satisfying thing you ever do in that. The most interesting and the most intriguing thing you ever do with differential equations. And actually, it's highly recommended to use the Laplace transform with differential equations at some point. It becomes quite inelegant to use the method of unknown coefficients at some point. So we're going to discuss that. And then, of course, we're also going to discuss the Laplace transform of y prime, which it's quite a neat result. So I think you're going to enjoy it. So yeah, see ya.